Okay, let's see. The first thing that's due is programming assignment 2, which is the end of this week. The second thing that's happening is the midterm on November 7th. And the third thing that's happening is homework 3 is due on the 15th. It's a busy class. Lots of stuff to do. Many questions about the announcements? Today's plan is to talk about collision resolution for hash functions. Because we realize that we can't prevent them, we have to resolve them somehow. And then we'll talk about introducing B-trees, the next data structure we'll talk about. But before we do, we have to warm up. And so you remember there's basically 2 resolution strategies for collisions that we've been talking about. One is separate chaining, which is the one we talked about last time. That's what's shown above. That's where you create, when you hash something to a slot that's already occupied, you don't worry. You just tack the new thing onto the end, or you put it onto the linked list. The other option is to use open addressing, where you don't allocate any new memory locations. You don't allocate nodes for a new linked list, for example. Instead, you just add things into the existing table until it really fills up, and then you have to resize. So I have a question for the warm-up. The warm-up question is, okay, this is chaining. This is separate chaining. So the question is, when you look at this thing, this particular picture, you notice that A and D hashed at the same location. Which one was hashed, which one was inserted first? Either A or D. You understand how this works, right? When I do an insert, I calculate the hash function of the key. I go to the table, and I insert the item into the linked list that's there. Maybe it's an empty linked list, but I insert it into that linked list. And if there's a find operation, then I go to the link, I hash the key, I go to the table location, and I look down the linked list until I find the thing that I want to find. That's the way it goes. How many people think A was inserted first? How many people think D was inserted first? How many people think that I sort of misled you in my description of insertion? Because I missed the key spot in the... the answer to this question is we really don't know. I mean, you could do it either way. You're saying, well, that's wasteful if, for example, I have an extremely long chain in one of these. This thing just keeps going on and on and on. If I call insert and I happen to hash to this location, I would be foolish to walk the entire linked list to insert it at the end. Wouldn't that be stupid? How many people think that might be stupid? It's kind of stupid, except for one thing. Hash tables don't like repetitive keys. So when you hash a key into a hash table, you actually have to make sure it's not there already. So basically, insert performs find to avoid duplicates. So I originally thought I was so clever coming up with this example and asking you which one was inserted first, but I thought, great, it'll remind you about the fact that we can insert at the front of the linked list really quickly so we don't have to traverse the entire list. But then it occurred to me we have to traverse the entire linked list anyway, because when we insert something, we want to make sure it's not already there. So if I do an insert of D, for example, the hash table should not put in another copy of D, or else it masks the existence of the second copy of D. So a responsible hash table wouldn't do that. Yep. Oh, that's understandable because I wrote it in tiny font. This says insert performs find to avoid duplicates. Is that better? Sorry. Yep.
So are the letters like the keys or the values?
A good question. The letters are the keys.
So what are the values? We don't know the values.
No. I at some point I told you that I was going to throw away the associated data with the key because I was getting lazy and didn't want to write it anymore. And then I just sort of continued to do that. So this is a key. And this is a key. But in reality, of course, you would have another field in that linked list structure that would actually hold the data. But this is a good question because one of the reasons that you're storing the key as well as the data is that knowing where the hash value hashes to, knowing where the key hashes to, doesn't distinguish what the key is. If I tell you you've hashed to location 1, you could have hashed to location 1 using key A or key D or perhaps key X, or many keys can go to that particular location. And so when you perform a hash like this using a hash table, you need to store the key as well in the structure so that you can check to make sure when you perform a find that you're actually finding something that's really the thing you're looking for. So you have to examine all of these entries to check if, for example, you're finding something like X, you say, okay, well, X hashed to this location, let's say, location number 1. Compare it to A, nope. Compare it to D, nope. Keep going until you have to compare the keys until you eventually find what you're looking for. Okay? Great. So now, if I perform an insertion into this, if I perform a find into this table, and the key is not there, then how much time does it take? Like X here is not in the table. It hashes to this particular location. How much time does it take? Yeah. In the worst case, order n, the number of things in the table, because they could all be in that slot. But a more specific question, once you know which slot it goes into, is the length of the list. The number of things in the slot. And that exactly is the length of the list. So the time that you perform in order to look for something that's not in the table is the length of the list. Okay, and that reminds us about what we were talking about before. The length of the list in each of those slots, if you have a really nice hash function which spreads everything out nicely, which of course you can't guarantee, but if you've chosen a random one, a random hash function from universal family, you sort of get this behavior, is the number of things in the table divided by the table size. That's the length of the linked list that's in a particular slot. And so when we perform an unsuccessful search, then of course the number of items we examine is expected to be alpha, the average number of items that are in each slot in the table. If we have a successful search, then there's one slot, or this one corresponds to the fact that we find the element. So here's our linked list that's out of this hash table. And someplace along this linked list we find X. And that is one piece of the cost involved in a successful search. But there's also n-1 other elements and how many of those are in this same slot? About, on average, assuming nicely spreading random function hash things. Could n-1 things, other than X, I've got m slots, how many things could be in that slot? Yeah, n minus 1 other elements, and about approximately 1 out of m of them hash to the same slot. I'm going to call it our slot. It's the slot that we're in. Our slot. We meaning the successful search. Okay, so we would expect that about n minus 1 over m of them would be in there. But this says n minus 1 over 2m. Why is that?
Because, like, on average, you're going to have that in the middle.
Yeah, so if I said that these elements are inserted in some, random way, then the number of things that precede x is about the same as the number of things that follow x in this linked list. And so about half of them of those precede our item. And that's where this 2 comes from. So you have n minus 1 over m things, and about half of them precede the thing we found, x, in the table. And that's the number of steps in a successful search. Yep.
Also, so on average, each slot has n minus 1 over m elements in it?
No, on average, each slot has about n over m elements.
Oh, n over m elements.
Yeah, every slot has about n over m elements.
Oh, and then you're saying, and then also, like, on average, we tend to find the key that we're looking for in the middle of the list. In the middle of the linked list of the slot.
That's what I'm saying, yeah. That's actually assuming some sort of other randomness that's going on here, but that's essentially what's going on. There's randomness about the order in which they're going to appear within that list. That's assuming that the insertions have occurred in some sort of random order.
So the thing that we want tends to be in the middle.
Yes. If things were inserted in random order, then you would expect that half of the things that were inserted came before that item and half came afterwards. I'm trying to explain this this weird function here in order to give you a feeling for why this is different than the weird function, which isn't so weird, whoops. Why it's different than this not weird function for when there's an unsuccessful search. Generally you would expect it to be like an unsuccessful search examines alpha and the other one examines something like alpha over 2, but it's not quite like that. It's about 1 plus alpha over 2, because you found something successfully and you have this alpha over 2. And then there's a little bit off. It's like minus alpha over 2. Everybody got this, at least somewhat? Okay. So the bottom line here is the bottom line on the slide. We want the load factor to be small because the load factor is what kind of dictates the running time, at least if we assume nice properties of the hash function and nice properties of the inserts. Okay, so if we keep the load factor low, everything is good. For open addressing, this is also the case. We have a load factor associated with open addressing, but it's a different scheme for storing the items in the open addressing table. In open addressing, we don't allocate new memory on insertions. So when you perform an insertion, which is described right there, you'll hash the item to a slot, and if that slot is occupied, well, you look for another one. You look for another slot which is not occupied. You have to follow a particular pattern of slots. You have to examine them in some sort of order. Perhaps the simplest one to think of is just examine the next one in the table. So add 1 to the index and look to see if that's empty. You have to do that because find has to find this thing after you've done the insertion. But anyway, you just look and see. You try the next possible slot. You try the next possible slot until eventually you find an empty slot. And at that point, you insert. And then the complement to insert is find. Find will, again, hash the key to a particular location. Let's suppose that it hashes here, and the key is X. Then X will say, oh, I'm trying to go into a slot that's already full. I have to look for another slot, and maybe what it'll do is it'll do what we've just said is this sort of simple scheme, which is look at the next slot, but that's full as well. So then it will look at the next slot, which is also full, and then it will look at the next slot, which is also full, and then it finally will get to the point where it can insert X, and that's where it puts it. Is it clear? So this is one. Yeah, do you have a question?
Doesn't this break if we were listing thing in one place? Because we'll stop at some point, like if we're looking at something above, but just think it's empty. It's not there. We'll find it at the moment.
This is a wonderful question. So the question was, doesn't this break if you try to remove something from the table? Because, for example, after I've inserted X, I decided to remove E, and I removed E from the table, and now I tried to find X, what would happen? I check to see if X is here. Nope. Here. Nope. Here. Oh, it's empty. Must be done. How could we possibly fix this? Yeah.
I heard resize back there, but I think that's the right answer.
No, resize is part of the answer, but resize is kind of brutal. If you have to resize every time you perform a deletion, that would be catastrophic.
I was going to say initialize all of the things from null value.
Yes, you've invented tombstones. Here, I spent a long time finding this. There you go. Use tombstones. Actually, I didn't find it. I drew the little tombstone thing and put a skull in the middle. Isn't it cool? A tombstone. You put a tombstone in place of the element. You don't erase it. You put that tombstone in place of E. So instead of erasing E, you put in that great picture with the little skull, which I can't draw. But anyway, it's got two eyes. Looks like a hat. Anyway, you put a hat into the slot, so that when you go through and you insert something again, or you find something again, you know that something's been removed. And so you keep searching. So the tombstone says, there's nothing here, but there was something here. Keep going. And that means that the find operation will keep going and eventually decide that it can find X. It will find X. That's an excellent question. A great question. And then the resize comment. What's the problem with tombstones? They take up space, and they're not any data. So eventually, if you keep removing things from your hash table and inserting new things and removing things and inserting new things, pretty soon you'll use up all the space with tombstones. There won't be any space for real data. So that's not good. And so resize allows you to throw away tombstones and rehash everything that's real data in the hash table, and also expand the hash table size if needed. And then you can proceed. So resize is part of the solution to this problem, because you have to clear the tombstones at some point. Okay, let me ask the same question I asked before, though, just to make sure everybody's on the same page. Which element, A or D, was inserted first? A? D? This is another one of those trick questions. No, it's not. I mean, for this one, I have a little arrow that tells you this is where it happened. A and D hashed to the same location. They both hashed to this location. And the first one there gets the slot. So A gets the slot. Now, again, you have to do a find operation to make sure that D is not in there. But basically, at that point, you insert it at the end. I mean, you could, I suppose. Yeah, maybe it is a trick question. You could I suppose, shift everything in anticipation of being able to insert D. But that seems ridiculous. Because what if you found D? Then you'd have to shift everything back. It was, anyway, so probably A inserted before D. This is when hash of A equals hash of D. Okay. The other sad thing about open addressing, besides the fact that we have to use tombstones, which is not sad, it's kind of fun. But the other sad thing is that we run out of space. So there's this thing called the pigeonhole principle, which we talked about maybe last time. Maybe not. But anyway, if you try to hash more than m items into a hash table that has m slots, it's not going to work. You can't put more than one item into a slot for an open addressing scheme, and there must be two things in the same slot if you have m pigeons flying into m fewer than, no, if you have m plus 1 pigeons flying into m pigeonholes. So that's bad. But, you know, that's not a property of chaining, because chaining can take more things without resizing. It can swallow as much as you'd like. It just changes the load factor. Here, there's a hard limit. You can't put more than m things into the hash table. Then you have to resize. Okay, but the advantages are that the hash table memory is allocated once, and that means that you don't have to do calls to the memory manager when you insert new items into the table. You just have to use already existing empty slots. And we have to understand its performance in terms of the number of tries, the number of locations we have to look at when we insert a new item. That's sort of the performance of these hash tables. Okay, is it good? Open address, yeah. You could overwrite this new stuff with do that. Yeah, you definitely could. And in fact, that's what you would do. But still, the case is that sometimes you'll fill it with sort of what they call orphan tombstones, things that nothing hashes to. They just end up taking up space in your table. And then, that's not. Actually, it doesn't matter. Who cares if they're orphan? So we could just insert them right over the top. Let's think about that for a second. If I wanted to insert something, I still have to do the find, to look through all those tombstones to make sure that the thing is not already there. But if I went over a tombstone, I can insert something right on top of the tombstone. Yep, that's one. Still on my tombstone. I still don't. Need wasteful. Pardon me? They're hard to draw. It was actually kind of fun. I must admit, I learned something doing it, so that was cool. That's a good question, though. Okay. Here's one scheme. This is called linear probing, which is the one that we just talked about, which is where you look at the successive entries in the table if you run into a collision. So this is a quick example of how to do that. The hash function we're using is k mod 7. So keys are integers. And the probe sequence is defined by that function. That function, which is on the ith try, we look in hash k plus I mod m. So that's just saying on the 0th try, we try sticking it in hash of k. If that doesn't work, then on the next try, we try hash of k plus 1 mod m, etc., until we find a place to put it. So this is just a mathematical way of saying exactly, look in the next slot and see if it's empty. So here we go. We insert 76. 76 mod 7 is 6, and we succeed in putting it into location 6. The little circle that's empty is success. The little circle that's not empty is failure. So now we try 93. 93 mod 7 is 2. It succeeds in getting into location 2 because nothing else is there. Then we try to insert 40. 40 goes in perfectly fine as well. But now when we try to insert 47, 47, of course, hashes to the same location as 40 mod 7. And so we get a collision here. And we have to try again. And we try by incrementing the index by 1, following this scheme. And we go to here. And then we increment it by 1, but of course we're taking it mod m, so we go back up to the top. And there we find the spot where we put 47. Okay, you got it? Yeah.
So hash of k returns k.
Hash of k returns k mod 7. So this is saying, like for example, 47, 47 mod 7 is 5.
Yeah, but that whole function is hash k. Hash of k.
No, this function is hash of k. The whole function is a sequence of values. If I increment I, starting with I equals 0 and go from 1 to 2 to 3, 4, it's called a probe sequence. So this function defines a probe sequence. And so it's not just one value, it's multiple values.
Because I thought the hash function, the definition was the one that you took to go from a value to the index and place it in.
No. A hash function is simply a way of getting the key value into an index into a table. But for this type of hashing, this open addressing hashing, it might be that that slot is occupied. So you're not going to put it in the place where the hash function tells you to go. You're going to have to follow a sequence of locations which depends on what's been inserted before. So it can't be a function that's completely independent of anything but that particular key value. It must depend on what's already there. And the way to do that mathematically, or the way to describe it, is to say that there's a sequence of positions that you're going to look at. And that's defined by this function. It's a probe sequence. Yeah.
So can you think of the I as like hitting each one and then incrementing it if there's a collision? So like hash k mod m is like the initial one, and then plus I equals 1, and then plus I equals 2, like go to the next sequence until you find an I that is at an empty slot.
That's exactly right. Yeah, you can think of I like to think of I as being the try. How many tries have you done so far? 0 or 1? If you've done 0, then I is 0, and you just try hash k plus 0. And then the second try, or the next try would be try 1, hash k plus 1. Yep.
Also try to insert 40 examples. For the first try we took 40 mod 7. And in that case I equals to 0. So then if we were to relate the general expression to that specific mod expression, so hash k would return 40, right? It would be 40 plus I, where I equals to 0.
No,
So the whole sum will be 40.
No.
Be mod 7.
no. Hash k is this. K mod 7. I'm using this weird percent thing because that's what C uses for mod. But I would have written mod if I'd done this again. So it doesn't matter if you take the mod before or after, but I'm telling you, whatever hash function you use, and this is a stupidly simple hash function, you would never use this hash function, right? Because you would choose a hash function at random from a universal family of hash functions. So it would be a more complicated hash function. But I'm giving you a hash function which is easy to compute for us. Computers have no problem with this stuff. Yeah.
Is m 7 in this thing?
M is 7. That's the size. It's always the size of the table, at least when I'm talking about hash functions. Okay, great. That's linear probing. There's an entire industry in generating different probe sequences for doing this type of probing, this type of open addressing scheme. Here's another one. There's lots of them. There's quadratic, there's Well, we're looking at double hashing. There's another one which I'm forgetting. Well, that's kind of sad. Anyway, it doesn't matter. You can create these different sequences. Yeah.
Which is more popular in industry, like shooting or
Which is more popular in industry? What industry are you talking about? For like desktop computers or for routers? Okay, because if you're implementing a hash table in a router, you don't want to allocate them. So you basically have a fixed size hash table and you use something like this type of open address. If you're in a computer, then you do something clever. You basically use you probably use a variant of these simple hashing schemes which allow for progressive expansion of the hash table as you use it. So the ones that are in C++, for example, are probably very complicated ones. I know that in most programming languages, the hash tables that are offered are kind of these progressive ones which expand gradually as you insert more things in it and don't incur a resize cost, which is sort of like garbage collection. It sort of pauses what's going on for a while, and you can get away with something different that will do this more progressive. But we don't talk about that sort of thing, sadly. You can teach a whole class on hashing. It's unbelievably cool. It's like Bloom filters, cuckoo hashing. It's like all kinds of crazy stuff you can do. And they're really good things because it's such an important problem. Okay, but we're going to do double hashing. Double hashing says, again, I have a primary hash function. I take that hash function, and on the ith try, I use that hash plus another hash times I. So what this is doing is it's saying the step size that I should use when I find an occupied slot is not always 1. The step size, how far I go down in the table, is this second hash function of k. Okay? So let's look and see what happens. Suppose that my hash function, again, is just this one. My primary hash function is just mod 7. My secondary hash function is this weird looking thing, which is basically take k mod 5, but subtract that from 5. Why would I do that? Why wouldn't I just take k mod 5? Why do we do this weird 5 minus k mod 5? Yep. Nope. I'm trying to give you a very easy to figure out example. So I want it pretty easy. Why? It gets rid of the 0. That's exactly it. If I took it k mod 5 and somebody gave me k equals 20 to hash, 20 mod 5 is 0. So my increment would be 0. That would be bad. It would mean that every time I missed, I would say hash k plus I times 0. And it would be the same place that I was before. So now you know the property of the second hash function. It has to be something that doesn't produce 0. So this is one way to ensure that it doesn't produce 0. Okay, so here we go. We hash 76. Again, 76 goes into this location. Now we hash 93. 93 goes into the same location. Now we hash 40. 40 goes into this location. And then we hash 47. Now before 47, we had to march down successively. When we first hash 47, it goes into the same spot as 40, but it fails. And now we increment by the secondary hash function applied to 47. And the secondary hash function applied to 47 is 5 minus 47 mod 5, which is 3. So that's the increment. And so we go, okay, 1, 2, 3. There we are. And we found the place to put this item on the second try. Or the 1th try, because there's the 0th try. Got it? Why do we do this? Why would you use a hash function for the increment that's dependent on the key k? Why is that a good idea? Why wouldn't I just have everybody increment by 3? So all keys, when there's a collision, instead of incrementing by 1, increment by 3. Well, you can see that there's a problem with linear probing. We kind of saw that problem in that we didn't see it on this picture, but we saw it on this picture, in that you create these long chains, and then these long chains grow bigger and bigger because they capture more stuff that hashes into the table until eventually they join up and become really long chains, and that's bad. That's called primary clustering, and it's so in order to avoid primary clustering, what you do is you don't do linear probing. You do something fancy like quadratic probing, where the only difference between linear probing and quadratic probing is that you increment by I squared as opposed to I. This means that the hops that you're making through the table are still determined by your trie number I, but it means that the hops are getting bigger as you go through, so you don't get this kind of primary clustering, this sort of merging of stuff as easily. We've stepped to double hashing, where not only are we making the increment different, but it's dependent on the key. Why would I do that? Why would I make it dependent on the key? Think about what happens when I have two keys that collide. So if two keys collide, and I follow a scheme like quadratic probing, which increments according to the trie number I, those two keys will never, ever split apart. They hash to the same location initially. The next place that they go to is going to be the same. The next place is going to be the same. It doesn't matter how many hops we take, it's always going to be the same. This double hashing tries to eliminate that possibility. If two keys hash according to the primary hash value to the same location, like these two, 40 and 47, there's a completely different increment for 40 as there is for 47. So if I follow those increments for 40, I won't be always in lockstep with the increments from 47. So different keys with the same primary hash value do not follow the same probe sequence. And that's good for secondary clustering. These words are, it's good for separating things that hash to the same location. If you have a lot of stuff that's hammering on one location, they will be spread out as long as you have the different secondary hash function. Yep.
But if two keys both have the same hash k value, then for the hash 2, you're also taking the mod 5 for both of them, so shouldn't that also produce the same output?
When would it produce the same output? What has to be true? So now you know that the key mod 7 is the same for both keys. They hash to the same location. Now what has to happen for them to follow the same pattern? That's right. They have to match to the same. They have to be the same mod 5 as well. So now they're not only the same mod 7, they're also the same mod 5, and that's not all keys that are the same mod 7. They don't have that property. So it tends to separate them. And now you shouldn't pick on my hash functions here too much, because I'm giving you easy to calculate examples. I am not suggesting that you rush out and write a double hashing using mod 5. In fact, I'm encouraging you never to use mod 5 as a hash function. Oh, except for one case, and that wouldn't be using mod 5. When would it be good to use a hash function which is always 0?
The
If the hash table only has one slot, this is true. You should only use a hash function that has value 0. But even if you have a hash table that has more than one slot, why would you want to program your code so that it always uses hash function 0? Seems like a stupid idea. It is a stupid idea if you're producing production code. You don't want it to go out there with the hash function being 0. But why would you want to program it so that it has a hash function of 0 when you're programming this stuff? Testing. You want to make sure your collision resolution policy works, make everything collide. You want to test something that's always, you're always sure that there's going to be a collision. You always are sure that everything's hashing to 0. So when you're programming, often the first thing to do is and then you forget to take out the fact that you set it to 0, and then, never mind, that does never happen. It would never happen.
So if we don't use linear probing, then how does time work? We have like gaps in it.
Yeah. So if we have, again, when we perform find, we're going to take the sequence of locations that we look for the key in to be defined by this probe sequence. So I bring in a key value, and it tells me it's got a hash k value, it's got a hash 2k value, and now I know the sequence of probes that I would follow.
Okay, yeah.
And then I'll look in those positions. That's a good question. It's exactly the same as the linear probing, except that the sequence that's produced is different. The sequence of locations is different. Okay. Is it good? We already did this. Remove is interesting. Rehashing occurs when you basically, I should tell you something. What do you expect as the load factor increases? Which hashing scheme would you rather use? Would you rather use the original chaining scheme we talked about for large values of alpha? Or would you rather use something like double hashing or linear probing or something like that? What do you think is worse as an increase the load factor? Just the gut feeling is okay. How many people think it's that the chaining will degrade worse, like as alpha increases? Well, we know what it is. It's about alpha, right? That's how much cost there is associated with the find operations, at least unsuccessful finds in the chaining example. And I'm asking you to compare that cost to the cost of this sort of double hashing or linear probing scheme when alpha increases. What do you think is worse? How many people think that the sort of open addressing schemes degrade faster than the chaining schemes? How many people think the other way? Well, maybe one way to think about it intuitively is that an open addressing scheme kind of looks like a bunch of linked lists that are vertical. Right? You have a probe sequence that you're following for a particular item, and there's another probe sequence you follow for another item, and they're all using these slots that are in the table, but there's a sequence that you go through to visit. And the problem is that all of those linked lists are kind of like sharing the space. So as you get higher, as alpha goes up, as the load factor increases, you'll have a much higher chance that those sequences will start interfering with each other. Like the sequence for one item will also interfere with where I can hash another item. Whereas in the separate chaining, everything is separate. The chains are always distinct. And so for large values of alpha, it turns out this double hashing or linear probing, these things degrade much more quickly. They degrade like something like 1 over 1 minus alpha. and the other one degrades at something like alpha. So when alpha is small, it doesn't really matter, but when alpha gets bigger, it starts to matter. Anyway, both of them are sensitive to increases in alpha. I should write this down. Let's say open addressing. Let's say this guy, double hashing, for example, its performance is something like 1 over a 1 minus alpha for, let's say, for a find operation, where alpha, again, is the load factor. It's the number of elements that you've put into the table divided by the size of the table. Yeah.
Was it okay if you could explain again what you meant by saying that with this approach we sort of have this one linked list? And also like how the sequences might interfere with each other?
Well, we saw this happening right here. So I had two sequences, the AD sequence, and I had the, oops, I erased it. Anyway, this is the EB sequence. And right there, because those sequences happen to be adjacent, you start to see that even though those are two separate, those would be two separate linked lists in the separate chaining table. If I put them into an open addressing scheme, now all of a sudden the performance associated with items that hash to locations A or D or B or E, they now depend on both, the length of both. In fact, the length of this is of length 2, the AD chain, and this is of length 2, the EB chain. If I hash anything into the A location, it now takes 4 spots because it's got to traverse all of that stuff. So that's what I mean by these things interact. Two things that go to separate locations, like for example, A goes to this location, E goes to this location, those things now, anything that hashes to those locations is going to be impacted by the others. That's good. Yep.
Wait, so for open addressing, what do you mean when the load factor gets too large? You can't be more than 1, right?
Right.
So is it like when it gets really close to 1?
Or even not even that close to 1, like 0.6, 0.7, something like that, it starts to be bad. Yeah, it's always less than 1 because this wouldn't make sense if it was, if alpha was bigger than 1, then that would be a sort of a negative number, and performance is not really negative. Okay. So anyway, for both of these schemes, but for more so for open addressing, when the load factor gets above a certain point, which is like a half, or maybe a little bit more than a half, you want to rehash to resize the table so that you can, well, you can do a couple of things. You can flush out tombstones, you can resize and use a new hash function because maybe you decided that this hash function is not performing as well as you would like. You just select a new one at random from the set of universal hash functions that you've chosen. Anyway, there's a bunch of positive things that happen when you do the resize that are listed there, but essentially you understand what those things are. And you also understand that the resize operation is like a resize of an array, because it is an array. And a resize is going to be amortized order 1 time if you resize by factors of 2, for example. Some constant. Yeah.
So this constant threshold is like different every chain. Chain will be like 3 big.
Well, it depends on what kind of performance you want from your chaining. So as alpha goes above 1, that's about the average cost that you're going to spend in separate chaining for an access. If you're okay with that, then that's all right. It can go above 1. But typically what's done is that even for separate chaining, you keep the threshold below 1. You get close to 1, and that's not good. At least that's what people think.
So that wouldn't even be chain, right? Because you wouldn't have a chain.
Well, you would have chains. for sure. Remember, the birthday paradox tells you you're going to have change no matter what. Pretty much. Oh, we're done. Fantastic. We won't discuss hashing because that's just crazy. Next time we'll talk about memory hierarchy and B trees.